we go. There you are. Stream should be starting anytime soon. I'll get the link and post it.
I got it.
You got it?
I sent the other one, so.
Okay.
What about you, Sam? I'm in Astro, so I have that connection to dark matter. Okay. So just as a heads up, mine is more focused on machine learning and more on the data analysis. And I'm not an astro, so don't give me some difficult, dark matter theory questions, because I may not be able to answer them. But I'll try my best.
But so like, is this gonna be more about like the actual machine learning algorithms, or is this gonna be more like about dark matter section itself?
The machine learning algorithm, I'm doing analysis on the I guess you would know the DMC, the fast DMC and full DMC.
Did you do stuff with SuperSim?
Yeah, we had other people on our team generate data sets, but I just did analysis on the data sets.
We can probably get started on this.
Is it straight up?
So, yeah. Yeah. Just. Did you? Are you? Oh, okay. So, does the thing work? Okay. Can you talk for a bit just to check that the sound works?
Sure. Mic check. Mic check.
Yeah, it's.
Sorry, try again. Hello. Hello. Okay. Is anyone watching right now? On the screen? One watching now. That's all not me. I'll screen chat. She did say that she will on screen. Okay. I think we can.
Yeah, we can.
Okay.
Get started now. So yeah, it's going to be just like the actual oral exam. So you'll have like between 15 to 20 minutes for the actual talk. Then until like 5:10 or something, we're gonna open up to questions. Yeah.
Okay. I did tell Sam before you came, I have to rush to Ottawa after this, and I have to catch a ride like right at 5. So I'll try to be quick to give people some time for questions, but the presentation is about 20 minutes, 4:36. So I'll start now.
Okay.
Okay. Thank you guys for being here. Today I'm going to be talking about my research regarding the interpretation of detector signals using deep learning as part of the Stone Lab Super CDMS collaboration. So the goal of this project is to train and optimize a neural network in order to measure the location of energy depositions in a Snow Lab Super CDMS detector, and to eventually use this information to determine to improve the energy resolution of the detectors. So we build upon previous work done training on boosted decision trees using simulated data set. We investigate multiple neural network architectures on this data as well as on newly generated data. So before I get into the research, I'd like to cover some background information. Astronomical observations show that galaxies in our universe are moving at such high speeds that the gravity generated by the visible matter in these galaxies is not strong enough to hold them together, which leads scientists to believe that something else that we cannot see is at work. Dark matter is this proposed matter, and it's estimated to cover about 27% of the universe's mass. For reference, the visible matter in our universe makes up about 5% of the universe's mass. Dark matter does not interact with light. It doesn't absorb, emit, or reflect light, which makes its detection very difficult. But still, the possibility that dark matter could be composed of particles beyond the standard model makes its detection and identification one of the greatest current challenges in modern physics. So Snow Lab Super CDMS is a direct dark matter detection experiment, and it aims to detect the interaction of dark matter with normal matter detectors in a facility 2 kilometers underground. Snow Lab Super CDMS uses two types of detector materials and 2 types of detector designs, which are designed to measure, explore the low mass dark matter region. Yes. So when a particle interacts with the detector, it creates vibrations in the crystal lattice of the detector, and these vibrations can be quantized and measured as something called phonons. And the energy contained in these phonons contain information that gives us information about the amount of energy deposited into the detectors by the particles interacting. So the HV detectors, or high voltage detectors, are a type of detector used in super CDMS that emphasizes the measurement of these phonons. The HV detector has a high voltage of 100 volts bias voltage across the detector, which allows it to use make use of an effect called the NTL effect, which effectively amplifies the phonon amplitudes and makes it more sensitive. The HV detector is cylindrical in shape, has a radius of 50 millimeters and a height of 33.3 millimeters. And it has 6 detector channels on both sides, as can be seen on the right plot, on the right diagram. And the detectors channels on both sides are rotated at 60 degrees relative to one another. Yes?
Just curious, how many HV detectors are there in super CDMS? Like, still don't know?
I can't recall off the top of my head right now. There's multiple towers, and each tower has some number of HV and the other type IZIP, and then there's also 2 materials, germanium and silicon. But they kind of all work together to discriminate different kinds of events. So the other detector type IZIP focuses on ionization energy, and HV detectors amplifies the phonon energy. So kind of IZIP kind of helps it discriminate from things that the HV might amplify that might dominate over the things that you're trying to measure. So in order to simulate these detectors, the first step is to go through something called source sim, which simulates the particles that will interact with the detectors. And then the output from the source sim is used as input for the detector Monte Carlo, or DMC. And there's 2 methods, 2 approaches to DMC, the full DMC and the fast DMC. So the full DMC simulates the entire detector's complete physics. So it tracks the individual phonons, electrons, and volt pairs in the detector's volume. And it's an accurate representation of the detector's physics, but it can take hundreds of seconds to generate just a single event. So the fast DMC is an alternative approach which estimates the detector's physics and is useful for generating larger data sets. Afterwards, the output from the DMC, the raw data, is taken in by something called CDMS BATS, which processes and reconstructs relevant metrics known as reduced quantities, or RQs. So some examples of RQs would be the phonon amplitudes measured at each channel, as well as the delay in the phonon pulses measured at each channel. So previously, Aditi Pradeep, a researcher from UBC, generated a full DMC data set of an HV detector, and she attempted to reconstruct the X, Y, and Z positions of events, but she was unsuccessful using a neural network. You see on the plot to the left, her results are comparable to just a simple linear fit. So she resorted to using a boosted decision tree, which is another type of supervised machine learning model. And she found that she had better resolution using a boosted decision tree compared to linear fit and her neural networks. So just to cover the basics of neural networks, it's a supervised machine learning model, which means it takes in labeled data set and makes predictions on these labeled data, and then compares these predictions to the labels of the data using a metric called loss. So the lower the loss, the better. And it does this step by step after each traversal through the data set. And so this process can be sped up if you divide the data set into chunks called batches. So then one whole traversal through the data set is called an epoch. The neural network consists of multiple layers and neurons, and these neurons are combined and multiplied in different ways to give the neuron for the next layer. And this process continues until we get to the output layer. It's also important to note that the data set, a certain percentage of the data set is also set aside before the training, and this is called a validation data set, and it's used as a unbiased data set to validate the predictions. So now to get into my experiments. Using Aditi's data set that I described earlier of 10,000 samples of full DMC of an HV detector, we trained on multiple neural network architectures, and by assessing the plots like the ones on the left, which shows the regression of the loss over different epochs, we tuned the hyperparameters, or the parameters like the number of epochs, the batch size, and also the number of layers and neurons per layer in order to optimize this loss. We also found that normalizing the data before training gave us allowed our neural network to learn faster and with lower loss. So the following plots are my results, and it shows the predicted versus actual position. The X and Y are in orange and green, and the orange and blue, and the Z is green points on the plots. So it's important to note that Aditi's data actually included a different, more sophisticated type of phonon amplitude RQs as well. And she focused all of her training on those type of phonon amplitude RQs, which can be a little difficult to replicate and generate more data sets. So the top left is our results from training on those kind of phonon amplitudes that Aditi was using. And the top right is training on just the regular, the standard method of RQs for the phonon amplitudes. And we see that although they both aren't learning the Z very well, they both have comparable X and Y predictions. So from this, we can conclude that we don't have to rely on Aditi's new method of RQs, and we can just stick to the standard RQ, the standard simulation techniques, which allows us to generate more data sets. The idea of figuring out the location of an event from detecting the signals at multiple different locations, I found was analogous to how satellites for GPS and other LiDAR systems determine the origin of events as well. And the way these systems work is that they look at the time of arrival of the pulses or the signals at the different locations in order to narrow down the origin of the signals. So because of this, I was motivated to try testing on our neural network on training on the phonon pulse delays rather than the amplitudes to see how much it can learn. So the bottom left plot is when you train on just the phonon pulse delays, and you can see that it contains more information than the phonon amplitudes, and the neural network was able to learn the Z predictions much better. And then if you combine the phonon amplitudes and the delays together, so double the input parameters, it learns the best. It learns the X and Y, comparable, but the most improvement is in the Z predictions. So in order to train on a larger data set, Warren Perry, a researcher over here at U of T, generated a data set of 100,000 samples of a full DMC data set of HV detector. And since Aditi's data set was monoenergetic, meaning it's just a single energy value for all the events, this data set also had a uniform distribution of energy from 0.05 keV to 2 keV, so that we could make some energy predictions on this data set as well. So for these trials, we used the phonon amplitudes and the delays for the regular RQ method, and the output was the X, Y, Z, and the energy of the phonon of the detector events. So we see when training on the full, when making predictions on the fast DMC data set, we see some strange patterns in the predictions, and the X and Y predictions exhibit some sort of step pattern, and the Z predictions are mostly positive, or if not just above -5 millimeters. So the Z predictions is still kind of a puzzle to us, and we're still working to understand why the fast DMC data set has neural network predict has a bias towards the positive predictions. But if we look at the energy predictions of the predicted versus actual energy values, we see that most of the predictions are concentrated around the diagonal. So it shows that our neural network is learning and making predictions on the energy. And if we plot the predicted minus the actual energy, we can get the actual energy resolution as well, which is 0.21 keV. going back to the X and Y predictions, if we make histograms of the predicted and the predicted X and Y, so these are the one-dimensional plots on the bottom, and also a two-dimensional histogram of the predicted X and Y. We can see that the predictions are kind of concentrated at specific peaks, and these are separated by 60 degrees. So in order to understand this further, we can look at the FastDMC data set. So the plot to the very left is the phonon amplitudes measured by this specific channel. And we can see that there's very little energy leakage outside of the area of this channel. So the FastDMC really concentrates all the amplitudes at that specific channel. Since the channels on either face are rotated about by 60 degrees, the channels on the other side will basically just look like an inverse of this diagram. So if you overlap both of these, you see that there's areas of high concentrations of phonon amplitudes, but there's also areas of contradicting phonon amplitudes. This kind of explains why our neural network is predicting in these high concentrated areas. The areas of high predictions are where there's like high confidence of phonon amplitudes. And then the areas of low predictions is where the neural network kind of gets confused because it gets conflicting data for the X and Y positions. Comparing this to our full DMC data set and results, if we make a similar plot for the full DMC data, you can see that it's not concentrated at a specific channel, it kind of spreads more evenly throughout, which allows our neural network to make more even predictions throughout the whole surface. It's not concentrated at the 60-degree intervals. So in conclusion, training on we learned that training on just the standard RQs is sufficient and that we don't have to rely on any new advanced methods of reconstructing RQs. And we learned that phonon delay information carries a lot of information. So we get the best results when training on the phonon amplitudes and the delays. And we also see that when training on the FastDMC data set, we can see what the limitation of the FastDMC is, which can provide insights to future improvement of the FastDMC simulation. As a next step, I'd like to further investigate the FastDMC data and the predictions, more specifically for the Z predictions, to figure out what's going on over there. And I'd like to also create a full DMC data set that includes a broader energy spectrum so that we can test our neural network on the full DMC energy predictions as well. That's all I had to share for you guys today. Thank you for your time.
So, so that was actually pretty good in terms of time, 4:51. Yeah, so they're not gonna mark you down on that.
Yeah.
Yeah.
I actually just did my exam already.
Oh.
Yeah.
Yeah, okay. Well, I was actually gonna ask a few questions, kind of like, what they're gonna ask on the exam, but that doesn't really work very well.
Thank you.
Just did. But, go back to slide 18. I noticed something. Yeah. So, no, actually between slide 18 and slide 19. Go back. Yes, there we go. So, what exactly does PDS, PES, PCS1 mean? Like, I mean, is there like a physical difference between each one? Is probably like the materials being used or the detectors being used, or are they just like general regions?
These are just the labels of the different detector channels. So, like these channels, they just have different names of the channels. And I guess my research wasn't concerning the actual physics of the detector, so maybe there's a better reason for why these they have these labels, but these are just the labels for the different detector channels. And then on the other side, it would just be like PDS2, PDS.
But the reason why I was asking is that I might have missed something, but like, did you like train more on just the PCS1 detector? Because what I'm seeing across everything is that they're almost always like in that region.
So this was trained on all of the channels, on the data from all the channels, just to make the visualization easier. I just focused on this one channel. But if you have this overlapping pattern and it continues all over, you would see that you get like concentrations like this, like we see in the predictions.
All right. Okay. Yeah, that's the first question I had. Yeah, that's do you have any? I'll see if there's probably any questions in the chat.
Yes, I had a question. In the loss graph that you showed, where you had validation loss. Yeah. So if
the training loss, yeah, that's decreasing, the validation loss also, but like, it's big piece, a big spikes in validation loss. I don't know what that is.
No, not really, that's usually. Yes,
Have you thought about or tried to run it from more than 100 epochs? Because it seems to me like you could squeeze a little bit more out of your training loss.
yeah, I found that it kind of just, it takes, first of all, it takes a really long time to train.
Mhm.
And I found that, on the graph, it seems like it's going down, but even just after 50 epochs, it's not much difference.
Mhm.
So I thought it would be a better use of my time to just stop it at 100. I don't think it's gonna learn anymore than this, to be honest.
Now, I'm not really that much of an expert on neural networks, so this might sound a bit like a bit of a dumb question, but why is it that we sometimes have validation loss peaks at like, say, for example, like 30, 80, stuff like that?
I can't explain either. This kind of just from different trials, there's different peaks and it kind of just happens randomly. Because it depends on the data that it trains on throughout this process. But like if I were to run the algorithm again on the exact same data, the exact same neural network, the peaks might be lower, the peaks might be in different locations. That's just, you kind of just have to look at the general pattern.
I see.
Well, it's mostly like random error.
Yeah,
Yeah.
you're sampling randomly across a validation data set. You're training on your training data set, which is where there's constant loss there, because it's always going to optimize against the training data set. And you don't necessarily know the values that's going to pick out of the validation data set.
That's why the peaks in the validation is higher, because it's unbiased. The neural network hasn't seen this data yet.
Yeah.
Okay. So,
Thank you.
Did you have another question?
no, I think I don't know.
Okay, well, thank you guys for your time. Thank you for the questions.
Thank you so much.
Yeah.
Yeah, good luck with, the rest of the semester.
Yeah, good luck.
No questions on that?
No, although we did have a few people watching online, so that's good. Yeah.
And there's Justin, I think, has one other person.
Yeah.
Okay, thanks.
Okay. Right then.
Feel free to take, some